And in this short presentation, I will guide you through what we do at Hazy. We basically create synthetic data in order to solve problems related to privacy issues. This is a summary of my presentation. To start with why synthetic data is important and how we are dealing with synthetic data. Then I will explain you what type of methodologies we have to generate synthetic data at Hazy. And then, very importantly, how we measure the quality of the data and the utility and the privacy of the data that is generated. Then I go through some use cases, and finally, I will guide you through probably the most important thing is how we use synthetic data to unlock innovation in organizations. So the idea behind synthetic data is to create data that looks like real, but is not real, and it will help you solve your problem without relying on real data. Why? Because real data has privacy issues. So we cannot disclose our bank transactions to third parties because that will put us in big troubles. So big organizations face this problem, how they can speed up the process of innovation, of building models in the data, without going through the procurement and all of these steps that are necessary, that may take a year to get data to the teams and make the models. So how we build synthetic data? Synthetic data is not new. It's something that we've been around for some time. The methodologies are also, some of them are new, but most of them are not particularly cutting edge. But what is important here is how we combine all of these elements and make it as a product scalable and easy to use in the organization. So the idea is to find machine learning models that we are able to reproduce the statistical properties of the data without looking too much into details of the data. So you get the overall statistics of the data comprised in the synthetic twin, but if you go through each of the elements, you will not find a match with the real data. So the fields, the postcodes, the location, the amount of transactions will not match real data. I will tell you in a minute how you can be sure that is the case. So, as I just mentioned, the big problem we have today is that due to all of the regulations that are keep increasing all the time, for large organizations, even smaller organizations, they struggle to make the most of the data without falling into these issues of privacy. Because each time you share data about your clients, about your users, about everything that occurs inside your company, you may well deal with issues that you have to be sure that that data is not exposed to third parties, and you cannot use it to make some sort of attack, like linkage attack, that may be able to identify what are the users that you are exposing it. So it's a big problem for organizations. And what you do at Hazy, you will create a model that sits on top of your data and will help you in this process by generating a version of your data that is as good as the real data, and will allow your teams, data scientist teams, to work on this. That is a big step towards speeding up innovation in terms of deploying the models. What are the use cases for the synthetic data? Well, we have several. The back testing, stress testing, training, as I mentioned, doing all sorts of cloud analytics. If you want to move to the cloud and you want to expose your data into the cloud, there's lots of difficulties in this area. By providing a synthetic twin, you will be almost sure that we are not getting into troubles. Data compliance, cold storage, and something that I will talk a bit more in detail in a minute about conditional generation. This conditional generation is very powerful because it allows you not just to reproduce your data, but to enhance it in regions that we don't have enough of it. For instance, let's say you are analyzing faces, as I was discussing in a minute. If you have just white faces, not minorities, ethnicities in your database, your models will fail to produce a good representation of the face. So with using this conditional generation, we will artificially generate faces of ethnicities, of ages, of whatever, that are not represented in your database. So in this way, you will get, you can say, a richer data set than the original one. I will go in a minute to the techniques that we use to make it happen. So by safer data, we mean that we don't contain any custom information. So this process has is a pipeline that has several stages. The first stage we do in making this work is removing also PAIs, personal identifiers, information that may be related to you, like names, addresses, related to a person. And then we also do another layer, which is removing this processing these attributes, like postcodes, for instance, where they may be maybe not unique, but they are sufficiently granular that you'll be able to end up in a very small set that for an attacker will be easier to identify which is the person in this set. So there are techniques to handle that. One of them is generalization. So we create a bigger bucket, we do a sort of aggregation of the data, so that you can be sure that even if the attacker wants to know which the person, will not be able to get to a group less than a certain number of rows. And then on top of that, to use the techniques that I will mention in a minute, that are statistical techniques that will be able to generate your data by analyzing the statistical similarities between the different columns. So this is, I mentioned, is a pathway to the cloud. So every company today has a strategy to go to the cloud, and moving to the cloud with synthetic data is much safer than with the real data. It's like testing the waters and making sure we are not making, if you make mistakes, these mistakes are not painful, or will not cost us a lot. So how we generate synthetic data? At Hazy, we have several methods. I will group them into three main categories, which the first one is STV, Synthetic Data Vault. It's a technique that has almost 10 years old. It's very simple to use and fast, but the results are not very good. If you want to do something quick and simple, it's the method you should try first. Then we have the Bayesian method, which is our best implementation we have at the moment. Basically, we create a Bayesian network of dependencies between different columns that we have in our data set. And since after this Bayesian network is built, then we can make inferences and generate new samples of data. It can be as many as you want. This data is relatively data efficiency, this method. It doesn't need many rows. It can be a few thousand, sometimes just a few hundred. The only issue it has is scalability. If you have lots of columns, when I say lots, I mean thousands, the method scales polynomially with the number of columns. So if you have thousands of columns, you may need to wait some time before it converges. And the third method is generative adversarial networks, or GANs. The beauty about GANs is that they can run conditional generation. As I mentioned before, you can condition the generator towards a specific class, a specific category. In the use case we worked in the past regarding fraud data, we were able to synthetically create new samples of fraudulent transactions. Fraud data, as you know, is a very imbalanced problem. It can be typically 0.4 or even 0.1% of transactions are fraudulent. And every machine learning that you will try to deploy under these circumstances will struggle, because if it gets all of the transactions as non-fraudulent, you will get 99.9% accuracy. which is completely useless because it doesn't make the distinguish between the fraud and non-fraud. By enhancing the fraudulent cases using the synthetic generator, we will be able to get a more balanced data set, and the model will perform more, not only more accurately, but also it gets more robust towards new points that may face in the future. So in terms of metrics, we have 3 sets of metrics that guarantees you that our data is a good quality. The first one is similarity. How similar is the synthetic data with respect to the real data? To do that, we use a mutual information score, which is basically how much a variable is able to explain another variable. In this case, it's column. How much column A is able to explain column B. And this number has to be the same in the original data as in the synthetic data. Okay? It can be categorical data, numerical data, it can be time data, it can be Booleans, everything. And the second one is overlap, histogram overlap. How much the histogram, if you put the histogram of your original data and you compare it with the histogram of the synthetic data, they should match. And there's a third one that I'm not included here, which is a similarity drift. Basically, you train a model like a light GBM or a random forest, and you ask the model to distinguish between the real data and the synthetic data. If the model is not able to distinguish one from the other, then it's because the data isn't distinguishable. So you can be sure that your synthetic data, your fake data, is as good as the real data. The second metric is utility. You may ask the question, how good is the data that you are generating? Because in the end of the day, you want to solve a problem. You can, for instance, the fraud case, you want to predict whether a transaction is fraudulent or not. So you better be sure that the models that your data science team will develop for synthetic data is realistic when you put in production with the real data. So basically, you train the model in your synthetic data, and you test it in the real data, and you measure how much. Of course, there's always some degradation because it's not the same as the real data. And you measure how much degradation you have from moving from the real data, from the synthetic data, to the real data. There's also other metrics like query score, like you query, you do a count, you do a SQL query with a count, and you count how many rows you get from a specific query or a set of queries, and you compare that numbers with the numbers you get on the real data, and they should match, because some of these tools may be just used for simple BI. And also feature importance. Any machine learning model, the features that you get, the order of the features should be the same in the real and synthetic data. And some models perform better than the others on this respect. Privacy is a bit trickier. Privacy is not so easy to explain and to understand as the two previous. But we have several metrics for privacy. I give you just one example of it. In this case, suppose we have a set of points, like represented in this chart here, that represents the real data. Okay? On top of it, we plot synthetic data, which is the blue ones. And then one way to evaluate how private is our synthetic data is to make a simple circle around a point and count how many real points we get in between this circle that you make on the synthetic data. Okay? And if you find, if the number of matches are lower than the risk, then we don't want to be too few points, because if you have too few points, then it may be identifiable. So we define the threshold limit where we say, okay, if you have less than a certain amount of points, then we exclude this because we think it's not safe, and then you get the remaining. And you can see that typically in this case we put 15 points, and you can see that we retain almost all of the data. In this case, it's for a Bayesian network model. We just exclude a tiny minority of the points. For other models, this is not the case. We have to exclude more points. But the message here is that there's always a trade-off between utility, privacy, and similarity. Okay? You cannot have a good utility and a good privacy. There's a trade-off between them. And where is the right trade-off? It depends on the the use case. So these methods has always to be attached to a use case on that. And then based on that, we have these parameters that you can fine-tune and get the best combination for your particular case. If you are very concerned about privacy, then you can create synthetic data that is very, very private. But of course, the utility of it will be lower because we are getting some degradation. On top of that, you can use also differential privacy. Some of these methods have differential privacy in it, and I will not go into details. So in terms of limitations, so using synthetic data is not the same as real data. We have always this dilution. That means that we are getting, the data is not as good as the real, and you need to be careful about that. The second one is that you cannot handle IDs or anything that is very, very granular. And this is, in most cases, not a problem because all machine learning problems do not handle these variables because they are too granular. And in terms of the data itself, we do not handle at the moment sequential data. We are working on models to deal with that. It's not easy. And again, the generator that you are building depends on use cases because different situations you may have to use different conditions on the generation. Finally, the GANs have a problem. There are several problems. Even if they are very powerful, they generate these beautiful faces that you see in the internet. One of the problems they have is that they have a high memorization capability. So you need to be careful because they can easily memorize points from real data. And so the privacy, in terms of privacy, they may perform worse than other techniques. So just briefly in terms of conditional generation, this is an example using the neural networks compared with other techniques. In this case, for the MNIST data set, as you can see, in the last row, GANs are much better because they generate much crispier image, and they capture the style of the image much more diverse from itself. And so compared with other data augmentation techniques, they are better. This is an example that I use for insurance situation where they want to model low-frequency events, and we use this technique for augmenting the minority class. In this case, we create fake claims so that the frequency model trained on this augmented data set perform better than without this augmentation. I think this idea of synthetization for conditional generation is very powerful. It will allow you this is an example again from NIST, but the idea is in the rows is a class. This is a number, 0 from 9, and in rows is a style. So you can see, the style can see different noise vector, it's a different style, and you can see that you can generate things that does not exist, okay? So you can make tricks like, what will be my customer? I have a customer, I have a company in UK, okay, insurance, for instance, and I have a set of behavior in my customers in UK. And you make a question, okay, if I move my company to France, or to Germany, or to Brazil, which is much different, how my customer will behave in Brazil, okay? Today, you cannot, no machine learning algorithm will tell you this because you don't see the data. But with this conditional generator, you can have a guess about what will be like your customers in Brazil. Just an example that I took from image, because this is very useful. It's very the most of use cases are image. It's called cycle GANs, cycle consistent generative adversarial networks, where you can transform zebras into horses and horses into zebras in a very nitty way. But the idea here is that you can have your model exposed to a set of scenarios in the left-hand side, and you can map it out to another scenario. It can be, for instance, data on your social media and data on your bank transactions, okay? So you can map to data sets without IDs. The thing is that they are not aligned. I don't know how to transform a zebra into a horse. The horse that I see here is different from the horse that the model is building. So it doesn't need to see the real data aligned, okay? So this is pretty much my presentation. We have already these models some of them are already in production, and I'm happy to answer some of your questions. Thank you very much.